Welcome. We were discussing about memory in embedded system, and in the previous video we have discussed about program memory or read-only memory and different variants of read-only memory. In today's video we are going to discuss about data memory or read-write memory, which is popularly known as random access memory, RAM. So basically RAM or random access memory is data memory of controller used in embedded system. So basically we call it as working memory, because when the system is in use, the datas are fetched from this memory. All the informations required are stored to or read from this memory. So we usually call it as working memory. So that directly tells you that the controller used in the system can read this memory or can write to this memory. But one important point here is it's a volatile memory. What does it mean? Volatile memory means when the power is turned off, all the contents, whatever the informations you have or whatever the informations you have stored in this memory during the working will be destroyed, will be lost. So data memory or read-write memory can be used to work on when the power is on. If you have any instructions to be saved, then you have to use program memory. That's why we call it as program memory, because the instructions are stored in that memory, ROM. So data memory is that memory which is used for working the system at that point of time. So your laptop or your desktop PCs or your smartphones all have this RAM. So you go for, in your smartphones, you go for 4 GB RAM, 8 GB RAM, 12 GB RAM, right? That makes the working faster, the processing faster. But the moment you switch off the mobile phone, the entire applications or required informations which are stored in ROM will be available for you after switching on the smartphone. The other informations will be lost. So this has to be remembered. So generally, random access memory is classified into three categories, that is static random access memory, dynamic random access memory, and non-volatile random access memory. So we started by telling that RAM is volatile, but with some design changes I can make it as a non-volatile RAM too, sometimes required in some applications. It will not be exactly like a ROM. Okay, there will be loss of some information, but we'll see in detail why it is known as non-volatile RAM. So the first category to be discussed is static RAM. The static RAM stores the information in the form of voltage. Okay, all the informations are stored in terms of voltage. For example, if I have a voltage of 4.2 volt or 4.3 volt, I say that I have a logic high information. If the voltage is 0 or near to 0, like 0.3 volt, 0.7 volt, I say that I have an information stored which is equivalent to logic 0. So if you want to store information like 10, 10, 10, then you should have a voltage across, okay, some storing device as 4.3 0 volt, 4.3 0 volt something. Okay, voltage levels vary with the technology. I'm just saying an example. Okay, so they're basically made up of flip-flops. You want to learn about flip-flops, right? It is either flipping or flopping, 1 or 0. Learn about this flip-flop. They are bistable elements, right? Flip-flops are bistable element, and there can be sequential circuits also. So these circuits are used to store the information inside a static random access memory. Okay, so as you can see in the figure in front of you, a flip-flop is basically used to do a memory cell, and it takes almost 6 transistors or 6 MOSFETs. It can be MOSFETs. In the figure you have MOSFETs. Okay, transistors or MOSFETs. When I say transistor, it is a general usage. Okay, I am not talking about bipolar junction transistor BJTs. When I say transistor, MOSFET is also a transistor because it is metal oxide semiconductor field effect transistor. It's a transistor. So I say that generally I say it uses transistors. Is that fine? You should not have that misconcept of I am using BJTs, because usually students think transistors are always BJTs and they directly jump into NPN, PNP configurations. Okay, so here we are talking about MOSFETs. Okay, so we have here gate, source and drain. So along with these 6 transistors, I would have so a lot of wirings required. Okay, buses, word lines, bit lines, lot of wires required. Okay, so this 4 transistors are out of 6 transistors. 4 transistors are used for building the latch or memory cell. Okay, and 2 of them are used for controlling. So if you look into this figure, 1, 2, that is Q1, Q2, Q3 and Q4 will be used to store the information, and transistors Q5 and Q6 will be used to control the operation. Because we have to control read operation or write operation, because a RAM can have both. You can read into this cell or you can write into this cell. Okay, you can read from this cell or you can write into this cell. So that is controlled by Q5 and Q6. Switching on and switching off Q5 and Q6 will give you that ability. And generally we say that static RAM is very fast in operation, is faster in operation, okay, compared to other memory, because of its switching capabilities. You know that you can switch on and switch off MOSFETs very fast. The switching frequency of MOSFETs can be controlled. You can use any technology to control the switching frequency, and you can achieve very high speed of switching in case of transistors, making our memory faster. So it is necessary for us to understand, okay, a little more about how this semiconductor level circuit works, okay, in a better way. So I have to visualize this static RAM cell. So as a part of the visualization, I can simplify the static RAM diagram which I have just shown you. So I can treat those 4 transistors as cross-coupled inverters. Okay, those 4 transistors which we have seen just now can be treated as a cross-coupled inverter. So this is my Q5, this is my Q6, and Q1, Q2, Q3, Q4 are treated as cross-coupled inverters. So I have here 1 as my information, I will get 0 here. If I have 0 as information, I can get 1 here. So I can retrieve 1 from here if this was 0, and I can retrieve 0 from here if this was 1. Obviously, so if I see if this line, this end is 1, this end will be 0, because this is an inverter. So I have here 1, I get here 0. The 0 is fed to inverter, I have this one. So you can see that bistable, that is 2 stable, 2 states, 1 and 0 are stable here. Getting? Okay, now have a look at this figure. Back to this figure, you have this write control as my bit line B lash, and I have this read control over here as bit line B. And as I told you, this Q1, Q2, Q3 and Q4 forms this cross-coupled inverter structure. So how I am going to access this information stored in this cross-coupled inverter? As I told you, I will have 1 here, 0 here, or 0 here, 1 here. So I have a bistable information stored there. So the access transistor control is through the connections to bit lines B and B lash. So if I want to write a value to the memory cell, then I have to apply the desired value to the bit control lines. So which are my bit control lines? In this diagram it is written as write control, read control, and here you can see by default it is bit line B lash and bit line B. So I will explain with respect to the main diagram, right? Okay. So for writing 1, if I want to write a 1 into this structure, means here I need a 1. Then what should I do is, I should make this line, bit line B, as 1 and this as 0. If I want to write a 1, then I'll make my bit line B as 1 and bit line B lash as 0. At the same time, if I want to write a 0 to this cell, I'll be doing the other way. I'll be making this bit line B 0 and I'll be making this bit line B lash 1. Okay, not only that, I should assert this word line, because this word line is connected to the gate of the MOSFET, both the MOSFET, right? So I have to assert this word, means I have to make this word line high. So whenever I am making this 0 or 1 according to the requirement, I have to make sure that this word line is high. So if I make, the moment I make this word line high and make this 0 and 1 or 1 and 0, the required bit will be written into the cell. Now for reading, if I need to read the content, which bit is stored there? If I want to read the content of the memory cell, I have to make both these bits 1. I'll make this bit line B lash 1 and bit line B also 1. I'll make this both 1, right? And obviously set the word line also 1. So if I make both the lines 1 and make this word line 1, my cell is ready to read, give me the data, so I can read the data. So I'll be reading it here. Okay, so this read control, write control comes from the word line, and I can read data and write data. Data to write comes here and data to read comes. But the major disadvantage, the operation looks very simple. Okay, so once you have this structure ready at a semiconductor level, it is possible for you to control bit line B or B lash and assert word line to read or write into this cell very easily. But if you want to increase the capacity, as you can see here, for a single bit, or I say 2 bits, because it can have both the states of same bit, right, 1 and 0. So if I want to store a bit or 2 states of a bit, I need this many structure. It's very simple. I need 6 transistors for storing a bit of information. So that makes this either a low capacity memory or makes it a high cost memory, because if I want to add more and more memory cells, I'm going on adding 6 MOSFETs and that many wirings for each bit of information. So it is huge amount of hardware which is required for me. So it is going to consume more space on integrated circuit also. So considering all that fact, I say that the SRAM has a very big limitation of low capacity and high cost. So the next variant is dynamic RAM. So in dynamic RAM, the data is stored in form of charge. Okay, so I have a single memory cell structure of a dynamic RAM. So it is made up of a single MOSFET. The gate of the MOSFET controls the read and write operation, and the capacitor acts as the charge storage. Getting? So if you charge this, so as I told you, the charge is the information here. Okay, if the capacitor is fully charged, I treat it as 1. If the capacitor is discharged or capacitor is below some threshold value, then I take it as 0, logic 0. That is the idea, very simple. Okay, so Basically, the biggest advantage of such system is high density. Okay, high density, when I say you have a single MOSFET or single transistor memory cell, so you can have a lot of such cells in a small area, and cost will be comparatively less, right, when you consider the static RAM. In static RAM, you have 6 MOSFETs controlling a single cell. 6 MOSFETs are required for single memory cell. Here you have a single MOSFET for single memory cell. This help you to have more information stored in smaller area. So I say that it's a high density memory and low cost memory. But what would be the disadvantage? You know that a capacitor is used to store the charges and thereby information. So what will be the biggest disadvantage? The stored charge will leak with time, right? You know that capacitor discharges when time passes by if it is not supplied with a required amount of charges, right? So I say that charge gets leaked off with time, and to prevent that, I should be refreshing the memory periodically. That is the meaning. Okay, I should always refresh the memory periodically so that this capacitor stores required charges to give me required information. So for that, I may require very complex controllers. So this dynamic RAM always have these controllers associated with it for refreshing the memory periodically. Okay, when I say periodically, don't think about 2 days, 3 days, 5 days. Periodically, when I mean, it is every milliseconds. Every milliseconds, because I may or may not supply this word line. Okay, this word line can be 0 or 1. So the moment this word line is 0, this capacitor is going to have, or it is going to shed the charges. I cannot always keep this high so that this keep on charging. The moment this side is off, the capacitor is going to discharge through the ground. So every millisecond or even lesser than that, I should be making sure that this capacitor is fully charged if the information is 1, and fully discharged or discharged below the threshold value if the information stored is 0. So I should have a proper controlling circuit for doing this, because it is not easy, or it is not always holding the capacitor at full charge, because if the information is logic 0, then I have to make sure that the capacitor is not charged also. So it is a good controlling circuit which I need for that. Okay, and as I told you initially, this word line is nothing but the gate of the MOSFET. So this gate of the MOSFET will act as a path line for both incoming and outgoing data. So at this point of time, I know what is static RAM and I know what is dynamic RAM. I am talking about single cell. You have to imagine such hundreds or thousands or lakhs of cell makes your 4 GB RAM or 6 GB RAM or 8 GB RAM. Please understand that. When I say I am talking about 1 bit here, 8 bits is 1 byte, and you are talking in terms of gigabytes. So just imagine how many such cells will be required for making a 4 GB, okay, a normalized 4 GB RAM for your smartphone. And that memory is not even consuming 1 to 2% or 2 to 3% of the total space of your smartphone, hardware space of your smartphone. Just imagine where is the technology. So there is a lot of things to understand, to learn, and to apply for you people. Interesting. So for your purpose of the course, I would like to compare SRAM and a DRAM cell at this moment. That is a static RAM memory cell and a dynamic RAM memory cell. Before that, I will also add some point here. That is, the first one is known as static and the second one is known as dynamic, because in the first cell, applied voltage, okay, across the transistor is measured to get the information. Okay, basically the informations are stored in terms of voltage and it is not going to change unless you alter it. So it is static memory. But when you come to the dynamic RAM, information is stored in terms of charge, and this, unless controlled, this charge keeps on varying within a capacitor. Okay, you know the properties of capacitors. So it keep on change, it can keep on change, and you keep on refreshing the cell. So either reason it is known as dynamic. It is not stand free memory. You should keep on refreshing it and the information keep on degrading or upgrading based on what information you have in the capacitor. So that's why the name dynamic cell. Okay, yeah. So in SRAM you have 6 CMOS transistors or MOSFETs, but when you come to dynamic RAM, you have a single MOSFET and a capacitor. And SRAM cell, as you know, does not require any refreshing or recharging, but DRAM cell always require a control or refreshing. So I say SRAM cell is less capacity because it is less dense. Okay, I need a 6 transistor space there for 1 bit of information, but in DRAM I can store 6 bit of information in the same space, if you agree. So I say that DRAM cell is high capacity. Because of the same reason, comparatively DRAM cell is less expensive, right? Because for storing same amount of information, DRAM cell is less expensive because I require less number of transistors. But when you come to operation point of view, SRAM cell is very fast in operation. So the typical access time is 10 nanoseconds or so. But when you come to DRAM cell, the typical operation time is around 60 nanoseconds or so. So this is 6 times slower than SRAM cell. It has the other advantages of storing more information, okay, less expensive, but the operation is slower here because I need refresh requirements here. I need to take the information from the capacitor. So because of that, it takes more time for retrieving the information. So the next category of random access memory is non-volatile. So this is interesting. RAM is always known to be volatile memory, right? But for embedded system applications, always, okay, in most of the system, you forget general purpose systems, forget about embedded system. In most of the general purpose system, we use dynamic RAM for random access memory, read-write memory. Okay, there is no doubt in that. But for embedded system applications where a lot of interrupts are into it, okay, where you need to raise the flag. So this power supply should not create any problem for such applications. Thereby what we do is, we basically connect a battery. Okay, so basically a non-volatile RAM is nothing but a normal RAM with a battery backup. And it will contain a static RAM based memory, okay, with a minute battery for providing supply to the memory in the absence of external power supply. So there can be cases in embedded system applications where you lose the power supply for few minutes or so. At that time, this battery backed memory will continue the operation till the power supply is restored. So you have to understand that it is still a volatile memory, because if the power supply never comes back, then this memory can work only till the battery supply is available. Even though I call it as non-volatile RAM, I am calling it in terms of the actual power supply. But still, it can store the information only if there is power, and power is given by the backup battery. So you please understand. Okay, so it is not like ROM. It is not like ROM. It is RAM itself. Right, getting? Yeah. Now the lifespan of such memory is expected to be around 10 years. Okay, and example for a 32 kilobyte NVRAM which I can give you is a DS1744 from Maxim. Okay, from Maxim Semiconductors. So that is one example for a 32 kilobyte NVRAM. So I hope different variants of random access memory which is used within the embedded system is clear to you. Okay, so I have used a general approach while explaining these memory, but it is up to you how you relate it with the embedded systems which you are going to learn. Okay, the moment you learn Cortex M3 programming, the memory related to Cortex M3, then you should be able to recollect what we have studied in terms of ROM and RAM. Getting? Thank you for watching.